All right, guys. So this video is going to help you with the problems from assignment 1, which have quite a few questions, not just about scales or heat, but about gases, molecules, right? In some of these, you have to use this constant, all right? The Boltzmann constant. That is when you want to find the kinetic energy of a molecule, which is 3/2 of kT, where T has to be in kelvins. Okay, so there is a question in the first assignment. I want to check it so you can see it. And what I'm gonna do is I'm just gonna put like another, like practice another. Yeah. So what's the kinetic energy, the average kinetic energy of an oxygen molecule with 280 kelvins? So it's quite easy. You just use this equation. And you do 3/2 of the Boltzmann constant multiplied by the temperature in kelvins. And the temperature in kelvins is 280 kelvins. So what we what we do is let's put this in here. Just to double check the numbers. Times 280. And it's very small. When we start finding the root mean square value of the speed of the molecule, that is when it's going to change. The energy is the same because it only depends on temperature, but the speed of the molecules, oxygen, helium, hydrogen, carbon, it changes because it does depend on the mass, on the molar mass in this case of the element, right? So hydrogen is the lightest element. So they will have the, at this temperature, it will have the highest root mean square value of the speed. All right. But here we just use 280 times 1.38 divided by 2 multiplied by 3. So I get about 579.6. So 579.6 times 10 to the negative 23 joules. That can be written, we have 3, 2 equal, let's say 5.80 divided by 100, multiplied by 100, times 10 to the negative 21 joules. Again, it depends only on the temperature, but the speed of the molecule does not. The speed of the molecule does depend on the molar mass of the element, okay, or molecule. So that's a question in the assignment. Let's do another one, one where you have to find the mass. For example, there is a question here where they ask you for the mass of a helium atom. I don't want to do it for helium. I want to do it for another element, but I just want to show you. How can you use Avogadro's number to find the mass of an atom, right? To do that, we are going to use the atomic mass given in the periodic table. So each element has its own atomic mass. So you want to find, let's say, the mass of And oxygen, this is still use oxygen. Oxygen atom. What we need is we need the atomic mass of oxygen, which I believe it's 32, but let me double check. No, it's 16, my bad. Oh, 32 will be for O2. So 16 grams per mole. You know, you can get the number of moles, and we're going to do a problem like that in a little bit. So that's the molar mass. So to find the mass of the oxygen atom, let's put O in there, will be the atomic mass. I'm going to label it like that, divided by the Avogadro's number. Okay? The Avogadro's number is 6.023 times 10 to the 23 atoms per mole. It's number of atoms or particles per mole. So we divide, if you think about it unit-wise, 16 G over mole over 6.023 times 10 to the negative 23 atoms per mole. And that's I'm doing that so I can show you how mole, and the number of atoms is just a number. So you get, oh, sorry, 23. So it's going to be quite small. And here you can see how, depending on the element, you start getting different masses. 16 over 6.023, I get 2.65. So 2.656. 2.656 times 10 to the negative 23 grams. If it was helium, it would be less because it's 4 grams per mole for helium. And it makes sense. The helium, hydrogen, they will have lower masses because of the lower atomic mass or molar mass. Okay? So not bad, right? So far, it's just application of formula so far, and not some of the concepts. Let's go back and let's do some temperature. I mean, we did an example in the previous video. But in the assignment, you have a question like this, where they give you different temperature scales from Fahrenheit to Celsius. I can put practice another and show you a couple there. Right? So how do we change temperatures? Always use a formula. And to be honest, you don't have to use 2 equations. You can just use 1. Celsius over 5 is equal to Fahrenheit minus 32 over 9. That's the one that you always want to use. There. Because if I'm given Celsius negative 200, let's just say my Fahrenheit, sorry, is negative 200. Okay? Fahrenheit. Yeah, like that. So Celsius over 5 is negative 200 minus 32 over 9. So this is negative 232 over 9. So Celsius is negative 232 times 5, 5 multiplies there, divided by 9. So I get negative 129 Celsius. That's Celsius there. Okay, now if I'm gonna go from Celsius to Fahrenheit, let's use 90 Celsius. Right, so you have Celsius equals to 90 degrees Celsius, which is almost the boiling point of water. So 90 over 5 is equal to Fahrenheit minus 32 over 9. 90 over 5 is 18. 18 is F minus 32 over 9. I multiply 9 times 18. And then I add 32, I get 194. So Fahrenheit is, yeah, 194 Fahrenheit, right? Yeah. Sometimes they put 90 degrees, but it's 194. So that's the temperature scale, nothing weird there. 2 questions about that in the assignment. Let's find the molar mass of the number of moles giving the mass of an element. I'm gonna use, we use oxygen already. Which element? Let's use iron. Use iron. Okay, iron has 56 grams per mole. So let's do that. So let's find number of moles of 20 grams of iron. So let's say you're giving a sample of iron. That's iron, equals to 20 grams. Let's find the number of moles, which we label it N. N is mass of iron divided by the molar mass of iron. Then, that's the molar mass or atomic mass, if you don't chemistry, right? So, mass of iron is 20 grams. Molar mass is 56 grams per mole. So grams cancels and you get 20 over 56. That's 0.36 moles. Now, can I also get the number of atoms for the iron sample? Yeah. To find the number of atoms, I do the N multiplied by the Avogadro's number. So that will be 0.36 times 6.023 times 10 to a power of 23. That's also in the chapter 10 of the textbook, by the way. 0.36 times 6.023, I get 2.16, 2.17. times 10 to the 23 atoms. Right? Let me see if you guys can see that. I think you can, but yeah. Okay, so that's how you do it. Again, it's just concepts that you probably have seen in chemistry as well. Let's now do some pressure, volume, gases. Okay, there's a few questions here. Let me show you the question I'm looking at. A container holds 0.6 meter cube, 0.600 of oxygen at a pressure of 4.3. Then you open the valve, and then at constant temperature, you increase the volume until the pressure is decreased to 1.5, 1.50. What's the new volume? So that's Boyle's law. So Boyle's law basically states that at constant temperature, the pressure times volume of a gas is constant. And that's because you have, and we're going to discuss that in thermodynamics, that's an isothermal process. In an isothermal process, the temperature is constant. And we just write P1 V1 equals to P2 V2. Now let me show you why is that. The ideal law for gases, I have another color here, is P pressure in atmospheres, volume in meter cube equals number of moles, the ideal gas constant, and the temperature in kelvins. If the number of moles of a gas doesn't change, that means that the mass doesn't change, and you keep this constant, then this has to be constant. That's why you have this. This is Boyle's law. Same if you keep, say, volume constant and an isochoric process. P over temperature will be constant, right? Of course, we're always assuming that the mass of the gas is constant, right? That's not always the case, but we're trying to assume that there's no gas leaking. So anyway, you are given in the problem 0.600 at 4.30. Perfect. And then it drops to 1.50 times V2. So easy, right? V2 is this times this divided by 1.50. $1.72. Perfect. Atmosphere. Yeah. No, sorry. Meter cube. So the volume also. The volume increase. Oh, sorry, the volume decrease. The pressure went up. Wait, the pressure, my bad, pressure, volume, P1, V1, P2. So pressure decrease, volume increase. Yeah. All right, so there you have it. All right. Then there's another one, the other problem where they give you the same. I'm looking at this one here where they give you a vessel with a volume in liters. Let's take a look what happens when you have a problem like that. They have you 6.75 liter container with 3.60 moles and a pressure in pascals. If the pressure is in pascals, then we have to use the same equation, but the R will change. The R has to be in joules per moles per Kelvin. That's 8.30, 8.31. It depends what value, how you're rounding it. Okay, the R constant. So we're gonna find the temperature of the gas and the average kinetic energy. So if we have the temperature, you know we can find the average kinetic energy of the molecule, right? 3/2 of kT. So that's basically using the ideal gas law, which some of you probably have known in chemistry already. If you haven't, that's fine. Let's see it here. So let's write the information. You have a volume of 6.75 liters and a number of moles of 3.60 moles. And a pressure of 1.60 times 10 to the 6 Pascal. You're probably wondering why it's so high. That's because the atmospheric pressure is 100,000 pascals. It's 10 to the 5. The atmospheric pressure that we're feeling right now at sea level is 10 to the 5 Newton per meter squared. That's the Pascal. Okay, the atmosphere is a unit created to make that equivalent to 1. Okay, and in chemistry, you use more atmospheres. It's a way to keep the atmospheric pressure at a very standard value of 1, to keep it easy, basically. All right. So the temperature has to be in Kelvin. So we're going to use PV equals to nRT. That's what we are going to use. So my pressure is in Pascal. Now, Pascal means that Pascal, and this has to be meter cube. Pascal times meter cube will give you units of joules. PV, and we're going to learn that in thermodynamics, that's an equation that we're going to use for work. And work is measured in joules. So we have to place the right units. So we also have the right units for temperature in Kelvin and the right units for R, which in this case, R will be 8.30 joules per mole Kelvin. That's the R constant. You can find that on the textbook, but just so you know. All right. P 1.60 times 10 to the 6 multiplied by the volume. Okay, so 1 liter is equal to 10 to a negative 3 meter cube. Because we are assuming the density of water to be 1 gram per centimeter cube, or 1,000 kilogram per meter cube. Okay, so if the density is 1,000 kilogram per meter cube, then 1 kilogram of water is, right? You can find the density by using, the density of water is also 1,000 kilogram per meter cube. So if you have the liter, 1 liter will be 10 to a negative 3 meter cube for the case of water. So it's kind of a relationship that we can use in also chemistry. All right, so I can use that. So 6.75 times 10 to a negative 3. That's the number of moles multiplied by R multiplied by the temperature. The temperature in kelvins, because of this, will be this times this divided by this times this. All right. So let's see. Three 61 kelvins. That's the temperature of that given gas. All right. And if I want to find the average kinetic energy of this molecule for this gas, then I just have to use the equation I used at the beginning, 3/2 of kT. All right. So, I mean, it's a video, so a recording, so you guys can stop it right now. I have to raise this for space, but let's just erase this. To find the, in part B, it's part A. Part B is the kinetic energy, the average kinetic energy, to be 3/2 of kT, which is 1.38 times 10 to a negative 23 joules per Kelvin multiplied by 361. So I'm sorry, so 7.47 times 10 to a negative 21 joules. All right. And there's a problem where you have to do a whole bunch of steps similar to this to find the molar mass, the temperature, and all that. Let's just see something here. Okay. What if you were interested to find the root mean square velocity of a gas? Of a molecule, sorry. Let's say, and this kind of extra, but this is important. So I'm pretty sure some of you are wondering, how is it possible, right? The root mean square is velocity is defined as the square root of 3RT over the molar mass of a gas. That's because you can have right? Now, where do you get the That's one equation that you need to know. And then, so you can replace M with molar mass times N. And then you change the K to R, given the definition of the Boltzmann constant. Right? Oh, Rn, sorry. And constant, you get that. So that's basically how this works. You can give it in terms of K if you want, but R, remember, a point joules per kilo per Kelvin, joule per mole per Kelvin. Yeah, there. Molar mass is in grams per mole. But this has to be changed into kilograms per mole. All right? Because we want this to be in meters per second. Kelvin and Kelvin will cancel, mole and mole will cancel. Joule over kilogram. Yeah. Right? Because 100 is what? Is energy. That's joule per kilogram. Yeah, the square root of joule per kilogram. That will be. So you want to have kilograms in the molar mass. So let's say that you have a temperature for hydrogen. No, let's do helium at 400 kelvins. And you have the same temperature for iron. Let's use carbon. Also 400 kelvins. So let's find their respective root mean square values or velocities. The molar mass for helium is 4, right? That will be 4 divided by 1,000 in kilograms, 0.004. So I will be 0.004 kilograms per mole. And for carbon, it's 12. So 0.012 kilograms per mole. So then the P for helium is the square root of 3 times 8.3 times 400 kelvins over 0.004. So calculator, right? 3 times 8.3 times 400 divided by 0.004, 2490. So square root of 2490. 000. So I need to take the square root of this. I get around 1578 meters per second, so quite high. It's about 1.6 kilometers per second. As a reference, the escape velocity for Earth is about 11 kilometers per second. So at a higher temperature, 400 kelvins is about 120 Celsius. At a higher temperature, you can probably reach values where the molecule can escape. Now, what about for carbon? Square root of 3 times 8.30 400 kelvins over 0.012. So that's gonna be less for sure because of the mass there. Three times 8.3 times 400 divided by 0.012. 800,000. So let's just do that thing. 800,000. So I got about 911 meters per second. So it's small, almost about half. So there you have it. Okay. The assignment 1 or problems that I already uploaded a video for problems for assignment 2. I'll be doing another one for phase change and then laws of thermodynamics. That should help you for the first few assignments. All right, guys. If you have any questions, remember to join the office hours, and I'll see you guys later.